Okay, so probably one of my favorite topics to teach about are Lewis structures, and we've talked so far about where we can find electrons in the orbitals, what different orbitals we might find the electrons in, electron configuration, and so we have a good idea of, or at least a grasp of, where we might find electrons in an atom. So where might we find the electrons in a compound or in a molecule? And in particular, we're going to be thinking about covalent compounds whenever we talk about this. But we're going to talk a little bit about how we might identify those. And you may have done Lewis structures before in a chemistry class and never thought about a Lewis structure that way. But in reality, it's telling us where the most energetic electrons in the molecule might be found, which is a really interesting way to think about it. It's just a way to specify where the electrons are located. And of course, it tells us something more about the compound, but I find that really interesting. Now, to be able to do this, to be able to figure out where the electrons are located in a compound or a molecule, we need to know a couple different things. And we need to be able to find a couple different things. And you're going to find, you might say, okay, I've done this before and I didn't like it very much, or I didn't do very well. I have pretty much a foolproof method for learning to write Lewis structures that I'm going to show you. And if you follow my lead on this, you're going to be able to get the Lewis structures right every time. But we need to understand first where the most energetic electrons are located. So where are the valence electrons, or how many valence electrons each atom in the compound will have. And it turns out the valence electrons are the highest energy electrons in an atom. They're the ones that are involved in reactions and bonding. When we talk about redox, the electrons that are transferred back and forth during an oxidation and reduction process, those electrons are valence electrons. And so we're going to start, and we're going to use oxygen as our example multiple times. We're going to start with oxygen and think about oxygen and the valence electrons that oxygen would have. And oxygen, we know, is number 8 on the periodic table, 8 meaning that it has 8 total electrons. But in terms of valence electrons, it's going to be quite simple to figure out and straightforward to figure out how many valence electrons it has. And we're going to count the S block and the P block from the left-hand side. What I mean is we're going to start counting at lithium and move our way over to oxygen. So that's going to look like this. 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. We're just counting from the left, counting each element as we move over. We're going to look at one of these down here where we got the D electrons in place, the transition metals in the way. We'll talk about that, one of those, in a second. But we're just going to count over from the left. And in particular, our next example that we're going to use is going to be selenium. Selenium is going to be in the same chemical family as oxygen would be. Oxygen's here and selenium is here. All right, and we're just going to count over from the left, except we're going to skip all of the transition metals. Those are D electrons. We're not going to count the D electrons as valence electrons. We're only going to count the outermost S and P electrons. And so if we look at selenium, we would go 1, 2, skip all the transition metals, 3, 4, 5, 6. So oxygen has 6, selenium has 6 valence electrons. We can think about this using the electron configuration that we just got done learning about. So we're going to start with, and I would like you to at least think about this. When you get into Lewis structures, you're probably not going to write the electron configuration every time. But for oxygen, we are going to. And remember, oxygen, we said, has 8 total electrons and 6 valence electrons. So for 8 electrons, that would be 1s2, 2s2, 2p4. 2 plus 2 plus 4 is 8. That gives us 8 total electrons. That would be oxygen. All right. Now, if we want to figure out where the valence electrons or which ones are the valence electrons, we would take the ones at the highest energy level. In this case, that's n equals 2. 2 plus 4 is 6 valence electrons. So you can get it directly from the electron configuration. You can get it from the periodic table. Now, we're going to start by drawing what we're going to call a Lewis structure for an atom. And a Lewis structure for an atom is going to tell us where the electrons are located in that atom. It's going to give us the same information that the electron configuration would give. So the first thing we're going to do is we're going to take and we're going to write the elemental symbol. For oxygen, that's O. And then we're going to take the s electrons from the valence and we're going to put them on top. So there are 2 of them. They're going to pair up on top. And then we're going to take those 4 p electrons and we're going to fill them in 1, 2, 3 different spots, 3 different p orbitals. So remember, we did an orbital diagram, right? So we could do 1s, 2s, and then 2p electrons. And we said the s fills 1 up and 1 down, the 2s fills 1 up and 1 down, the p fills 1 up, 1 up, 1 up, and then it pairs. And so we have the orbital diagram. We're going to sort of reproduce this orbital diagram. We're going to call each of these 3 lower sides one of those p orbitals. So we're going to start by filling 1 in that p orbital, 1 in that p orbital, and 1 in that p orbital. And we have 4 total. So where does the next one go? Well, it pairs up here. So now we've got the Lewis structure for oxygen right there that we've drawn on the paper. And don't worry, I'm going to give you the opportunity to practice this in the next slide. So my suggestion is when I put this next slide up, that you should pause the video and actually work through and try to write this. And you're going to see the same format's going to show up a bunch of times where I'm going to ask you to write, we're going to start writing Lewis structures of compounds. And I'm going to say pause the video right here, and then you should give it a try. So pause the video, try to write the Lewis structure for nitrogen and hydrogen, then come back and I will show you how to work through this. So, all right, so for nitrogen is 1s2, 2s2, 2p3. So if we wrote that as an orbital diagram for just the valence electrons, the ones past helium on the noble gases, so 2s and 2p, we have 2 electrons in the 2s, 1, 2, 3 electrons in the 2p. That's it. All right, so now we can write nitrogen. 2 electrons in the 2s, they pair up on the top. 3 electrons in the 2p, 1 of them there, 1 of them there, 1 of them there. Okay, hydrogen's a little simpler. It's got 1s electron, so if we write the 1s, it's got 1 electron in it. And so if we write the Lewis structure for hydrogen, it's just going to have 1 electron in the 1s, so let's put the 1 on top. Right, now you may say, I've written Lewis structures before for atoms, and we never specified between the s and the p, and yeah, maybe you didn't, but this is kind of a nice way to keep track and keep order with that orbital diagram and electron configuration that we learned about before. All right, so we want to move on and talk about a molecule. And I'm going to show you first a Lewis structure. We're going to look at the Lewis structure for ammonia. And there are a number of different things that we have to understand about it. First of all, we have all the atoms that are part of that compound. Ammonia has a formula of NH3. There's 1 nitrogen and 3 hydrogens. These nitrogen and hydrogen are both nonmetals, so this would be a covalent compound. We know atoms in covalent compounds share electrons. So the nitrogen and the hydrogens are sharing pairs of electrons. each one of them is sharing one pair of electrons. We represent those as what we call bonding pairs, and we represent them as a dash. One single dash is a shared pair of electrons. So each dash represents two shared electrons between those two electrons. The nitrogen also has other electrons on it that we're going to call a lone pair. Those are non-bonding electrons. They don't really have a big impact on the bonding, but they're still there and they're important, and we're going to understand in a little bit why they're so important. We're going to call the nitrogen, the atom that's in the middle, we're going to call it the central atom, and we're going to call the hydrogens in this Lewis structure, we're going to call those terminal atoms. They're ones that are sort of out away from the middle, and there's no bond that extends from them. They're bonded to this atom, then they're not bonded to another one. So that we call them terminal atoms as opposed to central atoms. And that's what a Lewis structure looks like. And we're going to get to the point where you're going to be able to write those with no sweat. Okay? At least hopefully no sweat. If you have sweat, I want to hear about it. So please don't hesitate to send me a message on Remind and say, hey, I don't understand something. Because otherwise, I'm going to be honest, if we're sitting in the classroom, I can tell by looking at y'all's faces. Here, sitting looking at my computer, all I can see is my own dumb face. So that doesn't help me any, and I always look confused. So, when we talk about this idea of covalent bonds, what's really happening? Well, it's two hydrogen atoms coming together to form this molecule, and the molecule has a shared pair of electrons between the two hydrogen atoms. If we remember, each hydrogen atom has one 1s electron, and so what's really happening is this 1s orbital on this hydrogen and the 1s orbital on this hydrogen are getting so close together, that those orbitals start to overlap in space. And when they overlap in space, those unpaired electrons on each of the hydrogen atoms come together and they pair. So we get this region right here in between the two nuclei of the two hydrogen atoms where there's a lot of electron density. A lot of electrons are there. That's the covalent bond. It's the overlap between those orbitals. And we talked about those orbitals before, and we talked about the shapes. But that's what's there. That's what the covalent bond is. It's the overlap. We can see this as well in other compounds. Like here we've got chlorine gas coming together. It just so happens the orbitals that would hold those electrons in the chlorine would be p orbitals, but the p orbitals can overlap in space as well to form that covalent bond. And so that can happen. And the reason why that this occurs is all because of the noble gases. And that's going to sound a little bit familiar because you'd say, okay, we looked at the noble gases before and we're trying to figure out what ions were formed. We're going to look at them again whenever we get to the idea of a noble gas. And so it turns out that, all atoms are trying to get to the stable place that the noble gases have. And the noble gases have that space, that stability, because they have a set magic number of electrons. And not often that I'll use the term magic whenever I'm talking about science, but I call magic because it's a special number of electrons. And if the other atoms can get the same number of electrons as the noble gases, they'll share in that stability. Okay? That's the same reason that we had for why atoms would gain or lose electrons, why they'd form particular ions. And so it's a similar reasoning. They want to get the same number of electrons as one of the noble gases would have. And let's just review or come back to or remember, all right, where the noble gases are located. They're all out here on the periodic table. All right. And so all of the atoms are trying to get the same number of electrons as those elements. So if we look on the periodic table and we said, okay, well, how many electrons do they have? Well, 2 or 8 or 18 or 36 or 54 or 86. But those aren't really the numbers that are really all that important. It's the number of valence electrons that are important. So if we think about something like neon, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Or if we think about argon, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. or krypton. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's no different for any of them. They all have 8 valence electrons. Okay, now wait. Some of you are probably saying already, what about helium? Helium only has 2 electrons. You're right. Helium is the special one. It's different, okay? Sort of in the same way that hydrogen is going to be a little bit different from the other nonmetals. Helium has 2 electrons. We call that, okay? And so helium wants to have 2. So hydrogen doesn't want to have 8 like the other elements, nonmetals. It wants to have 2 to be like helium. We call that, for hydrogen and helium, we call that a duet. For the other elements, we say 8 valence electrons is what we call an octet. So you may have heard of the Octet Rule. That's sort of where this comes from, those 8 valence electrons that the noble gases would have. Okay, all right, so that sort of gets us to the point where we have to start thinking about, or we want to be able to draw or determine what these Lewis structures might be for different molecules. So there are going to be a number of different steps, and I promise you if you follow these steps, you're going to get a Lewis structure that's going to be appropriate. And I'm going to talk a lot about the idea of appropriate Lewis structures. All right, Lewis structures that are appropriate, everything will have its octet or its duet fulfilled. Okay, there are some cases, I know there are some cases where the octet and the duet are not followed strictly. We're not going to worry about those nearly as much in this class. So first we're going to add up the number of valence electrons of all the atoms that are in the compound. We're going to determine which one is the central atom. That's actually pretty straightforward to do. We're going to connect the atoms together with bonds, single bonds, just one bond in between each of them at first. Doesn't have to be one bond, it can be a double bond. Then we're going to make sure the octet of all the atoms is fulfilled using some of the valence electrons that we have. Central atom is always going to be the last one to get its octet. And if there are extra electrons left over, they're going to go on the central atom, and they're going to go in pairs. And you might say, I have no idea what you mean by those 5 rules. Perfectly fine. We're going to show you a bunch of examples. I'm going to record a video, and the only thing that we're going to do are work through 3 or 4 different examples. So for this video, our example is going to be methane. Methane's a fairly straightforward Lewis structure. Okay, now this is where I tell you, you might want to pause, because remember the first step is figuring out how many valence electrons all the atoms have in total in methane. You might want to pause the video and figure that out right now. Okay, so what we're going to do with methane, CH4, is we have to not only find the number of valence electrons, but we have to find the central atom. Okay? Central atom is almost always the atom in the compound that there's only one of. That's not always the case, all right? But usually that's going to be the case. Now, that's not going to be the case for all molecules. Get very complicated and complex. But for the ones that we're going to look at, it's going to be the central atom is going to be the one that there's usually only one of. A lot of times it will be the element that's the first one in the compound or the ion listed in the formula. Carbon, when you see it, always a central atom, never going to be a terminal atom. Okay. Then we're going to arrange all the other atoms around the central atom. We're not going to worry about how we're arranging them at this point. Don't worry about the geometry. That's actually where we're going to get to next week. And then we're going to connect the atoms together with a bond or a dash. Those are following all those same rules that, I already gave you that list of rules. So, it's going to be very similar to that. So let's just work through this. All right. So we've got methane. Hopefully you went through and you figured out that methane has 8 valence electrons. That's great. Secondly, we had to figure out which of the elements here is going to be the central atom. We said normally it's the one that's first in the formula, and that there's only one of. In this case, it's carbon, and we know already carbon gives us a little hint because carbon's always a central atom. Then we've got these hydrogens. We're going to arrange them. I don't really care how you arrange them. I don't think that there's a situation where if you have a reasonable Lewis structure that I would take points off for the way that you have the atoms arranged around here, unless you really go out of your way to try to make it look funky or something like that. Then we're going to connect these together with a bond. Remember, a bond represents 2 electrons shared between the atoms, so that's 2 electrons shared between the hydrogen and the carbon. So now we have added with these 4 bonds 2, 4, 6, 8 electrons. So we're going to take the total valence electrons, we're going to take away the 8 bonding electrons, and we have no electrons left over. All right, so we don't have any more that we can add. So whenever you get to that point where you have no valence electrons left over, that a lot of times is going to tell you that you're done. Not always going to be the case, because we have to go back and double check. So let's double check. Do each of these atoms in this compound have either an octet, 8 valence electrons around them, or a duet, 2 valence electrons around them? So this hydrogen has 2 electrons. Duet. This hydrogen has 2 electrons. Duet. Duet. Not do it. Just do it, like Nike. This hydrogen has 2 electrons. Duet. This hydrogen has 2 electrons. It has its duet. Now for the octet, carbon, how many electrons would it need for an octet? 8. And it's got 2, 4, 6, 8. So we've drawn the valid Lewis structure for methane. That's it. Okay, that's how we do Lewis structures. We're going to look at a different video about going through and working through a bunch of different examples.